Sometimes it doesn't work and the video's all choppy, but we'll see. Okay. So we're going to do our introduction to hypothesis testing. Okay. So now we are going to get really into statistical inference. Is it way harder? It's I don't know. Some people might say it's harder, but I guess everybody.
Does anyone say it's easier?
I don't know if anybody's. Some people say they enjoyed the second part more than the first part. People do say that. Okay, so this slide comes from our first day in class, if you guys remember, and we talked about the basics of data collection and data description. We talked about observational studies, experiments, things like that, gathering our data, sampling, all of that, and calculating summary statistics. Okay, does that sound familiar? Okay, and then we talked about probability. We got into the rules of probability. We did all those probability problems, and we dealt with the binomial distribution, the normal distribution, and then we did sampling distributions. Okay, and then we brought those two together to make confidence intervals. So based on the mean of a sample, so that would come under data description, and our understanding of sampling distributions, we created a confidence interval. Okay, and based on the confidence interval, we were able to answer our very first inference question, which was, if I have one sample, or if I have two samples, do I have evidence that those do the respective populations have different means? Do I have evidence that they have different means or not? That was our first inference question. We're making conclusions about the population based on what we saw in the samples. Okay, so we brought together, the Y bars and the S for descriptive statistics and our understanding of sampling distributions together. Okay, so the rest of this class is going to be all about more statistical inference methods. Okay, it says a survey of the many methods of statistical inference. Okay, and that's where we're headed in the rest of this class. Okay, so I think when I talked about confidence intervals, I kind of got into how the sampling distribution allows us to make these conclusions and things like that. And for the rest of our statistical inference methods, we could go back to the sampling distributions and the rules of probability, but the math gets a little bit more complicated and a little bit more, I guess complicated is the right word to use. And so a lot of times I will just say, from our, maybe from what other statisticians or other mathematicians have done, we have these tests available to us, and they are statistically or mathematically sound. Okay, but from here on, we're going to learn many of these different inference methods and their applications. Okay, so I'm going to draw a little map of statistical inference methods, which will kind of give us a layout of the different tests that we will, or methods that we'll encounter for the rest of our course here. Okay, so statistical inference, and a lot of it comes down to what situation are we in now, or what is the appropriate test or method to use in the situation or that we encounter. Okay, so we will see many different tests and methods and we need to know when it is appropriate to use each one. So we'll just, I'm just going to write statistical inference. And we're going to have a, we're going to ask what kind of response do we have? So response being the response variable. Okay, what kind of response variable do we have? Okay. So when we did the confidence intervals for y bar 1 minus y bar 2, what kind of response variable did we have? We had a numeric response. Okay. And we'll also encounter methods for categorical responses. Okay. Okay. And with numeric response, we can also have a numeric predictor, okay, which is not the case for y bar 1 minus y bar 2. Okay, when we did confidence intervals for y bar 1 and y bar 2, we had a numeric response, but I don't know if predictor is the right word to use, but the thing that allowed us to compare one thing to another was that we had two categories, we had two groups. Okay, so we could have a categorical predictor. Okay, and so with a categorical predictor, if we have two groups, then what we can use is confidence interval for, and I'm running out of space here. Let's see how I can fit this. Yeah, okay, two groups. I'm just going to squeeze it in here. Confidence interval for y bar 1 minus y bar 2. So this is one method that you have learned. You got two groups, numeric response. We can compare y bar 1 and y bar 2, and then make conclusions about whether the respective populations have different means or not. Okay. We're also going to encounter the classic t-test. Okay. And we will have independent and also paired data. And I'll get into all of this stuff here in the coming weeks. So we have independent and paired. So that's with two groups. We'll also talk about what happens if we have more than two groups. And in that situation, we will use ANOVA. Okay. There's a lot more. There's more tests that we'll get into, but I don't feel like listing them all out. But we'll get into them. Okay. If we have a numeric predictor, the method you use, so numeric response and numeric predictor, the method we use here would be correlation and regression. Correlation / regression, those go together. So that's a numeric predictor with a numeric response. Meanwhile, so far, the only thing we've done so far is confidence intervals for y bar 1 minus y bar 2. Next week, we'll talk about the t-test in detail. And I'm going to just lay out some foundational ideas behind hypothesis testing today. Okay? But I just wanted to kind of give you this layout of where we are headed. So as I introduce these different methods, you kind of have a little bit of a framework to fit these things into. Okay? And then so on the other hand, that's with numeric responses. We'll also encounter things for categorical responses. Okay? Categorical responses, if we have no predictor and we just want to talk about the categorical responses themselves, this would be the chi-squared, and we call it the goodness of fit test. Okay, no predictor. The chi-squared goodness of fit test. Also, we have confidence intervals for p, for a proportion p. And if we have a categorical response, we can also have predictors. We can have a categorical predictor. And in that case, we have the chi-squared test for independence. I know, it all sounds like gibberish right now, okay? But I'll say, today we're going to learn about the chi-squared this test and this test, and maybe I'll refer back to this, and we could say, oh, in this situation we're doing this, okay? And then we're not going to learn, but I'm going to put this here, okay? So this is not covered, but if you have a numeric predictor, then this is called logistic regression. But it is not covered in our class. Okay? So, and logistic regression is actually, I wish there was maybe like 2 more weeks in our class. You guys probably are thankful that it's not, because that's 2 weeks less of material that you won't have to learn for the final. But I would like to cover logistic regression if I could, because a lot of times for, I don't know, disease research and things like that, you know, it's, does someone develop cancer or not? That's a categorical response. Did they develop cancer or not? And maybe you are trying to relate that to a numeric predictor, such as, you know, how many grams of oatmeal did they eat per week or something. And maybe you want to say if they eat more grams of oatmeal, your risk of cancer is lower, or something like that. Okay, so there's a lot of good applications of that, but we're gonna run out of time. So, all right. Anyway, this is where we're headed. I think it's great. Of course I do, but yeah, I love this class. All right. So what is this? This is Stats XL13. May. It's already May 7th. Slide 01. Okay. So let's go. All right. So we're going to get into hypothesis testing. And so hypothesis testing is another method of inference. And what we do is we first present a pair of hypotheses. Okay? And then we take our data and we ask, how likely are we to observe this data if we're going to call this the null hypothesis. So, you know, you have a pair of hypotheses. The first hypothesis, H0, okay, so this is one of the hypotheses. If the null hypothesis how likely are we to observe this data if H0, the null hypothesis, is true? We ask this question, okay? So right now this might just feel like gibberish talk, like what are you talking about? But I'll try to fit this into a way that makes sense, okay? And then based on the answer that we get to this question, okay, so we ask this question, how likely are we to observe this data, okay? Based on this answer, we make a conclusion. Based on the answer, we make a conclusion about H0, the null hypothesis. Okay, so let's, and the conclusions are, and let me just point these out. Okay, so if the answer to the question is, it is likely to observe this data, okay? So if the answer is, it is likely for us to see the data if H0 is true. If that's our answer, then we have no reason to doubt H0. Okay, so I'm going to just put all of this stuff out in the beginning, and then we'll do some examples, and I hope it will flesh out these concepts a little better. Okay, and on the other hand, so there's two possible answers. If the answer is it is unlikely for us to see the data, if H0 is true. Okay? Then the fact that we observed the data causes us to doubt or reject H0. All right, so let's put this into some context here. Okay, so keep this in mind. Do you guys have this in your notes? Okay, so we're going to maybe I want to just shrink this and copy this onto the next slide. Now this is going to be too small. All right, let's say let's say there's some game, and this is totally stupid, but let's say there's casino coin flip. And it's a dumb game. You just flip a coin, and if it lands heads, you win, and if it lands tails, the casino wins. Okay? Huh?
No casino would ever do that.
I know, but maybe they will if it's like if the payout is 95 cents on the dollar or something like that. So you bet, or maybe you have to bet $1.05, and if you win, they pay you $1. And if you lose, they keep your $1.05. Okay? And actually, the casinos, if people were willing to play that game, they'd probably have it. Okay? It's just that I doubt people would be willing to play because it's so simple and dumb that, and it's so obvious that you're going to not lose money in the long run. But who knows? People always think that they're going to be lucky at the casino, and that's why they play, right? But I could set up that game and say, hey, $1.05 to play. If it lands heads, I'll give you $1. If it lands tails, I keep your $1.05. And casinos would go for that because in the long run they would make money. Okay? But anyway, let's just say, so if it lands heads, you win. And if it lands tails, you lose. Okay? So the probability of a win should be 0.5. Probability of a loss should also be 0.5, right? This is what should happen. Okay. And of course, in casino coin flip, they would never let you actually touch the coin. There would probably be some machine that, I don't know, maybe you crank something and then it shoots up the coin or something, right? Okay, anyway. So let's say you play 10 games. You love this game. This is your favorite game in Las Vegas. You decide to play 10 games. Okay? Now, according to the rules of probability, we expect you to win what? How often? 5 times, right? 5 times out of 10. Let's say you won 7 times. Okay? So this happens, and then the pit boss comes out, and he says, you won too many times. I think you are cheating. Please don't come back to the MGM. You're not welcome here, or something, okay? Now, would this be a silly thing to say after 10 games and somebody winning 7? We would say, yeah, that's not proof that it's cheating, right? And what would your defense be? You would say, I'm not cheating. I just got a little lucky, right? It's the best defense you can use at the casino. Ah, no, I'm not cheating. I just happened to draw 4 aces here. You know? And so your defense, no way, I'm just lucky. Okay? All right, so essentially, we are setting up a pair of hypotheses, okay? We have 2 hypotheses. And I'll explain these in a moment here, but the null hypothesis is that the coin is fair and we are not cheating. No cheating. Okay? Or if we wanted to say this in terms of probability, we would say the probability of a win is equal to 0.5. The alternative hypothesis would be something is going on. We don't know exactly what. Something is happening, which is basically someone here is cheating here. Okay? And in terms of probability, we would write the probability of a win. We don't know exactly what someone's doing. Oh, not 0.7. But the probability of winning has increased to be more than 0.5. Okay? So these are the pair of hypotheses. And so in hypothesis testing, we ask this question. How likely are we to observe this data if H0, the null hypothesis, is true? Can we answer this question? How likely are we to see 7 wins out of 10 games if the probability of winning is 0.5? Do we know how to answer that? So how likely are we to see the data which is 7 wins out of 10, wins out of 10 games. How likely are we to see the data if the H0 null hypothesis is true? Meaning probability of win is truly equal to 0.5.
Not a binomial.
It is a binomial. So we know how to answer this question. We know how to get how likely is this. So the answer to this is 10 choose 7, 0.5 to the 7 times 0.5 to the 3. Right? Okay? And so we can do this calculation. Choose 7 times 0.5 to the, okay. And so here I get 0.1172. Okay. Now, if the casino accuses someone of cheating for winning 7 games out of 10, then they will certainly accuse them of cheating if they won 8 games out of 10, 9 games out of 10, or 10 games out of 10, right? So what it should be is, how likely are we to see the data, or something more extreme, meaning 7 or more wins out of 10, okay? So how likely are we to see the data, and I'm going to add, or something more extreme. So this would be 7 wins or more out of 10 games, okay? So then we also have to do 10 choose 8, blah, 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 plus 10 choose 9, blah, 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 plus 10 choose 10, blah, blah, blah. Is that okay? So I'm just going to have R do that for me, because I don't feel like actually calculating these out. So I'm just going to do sum of D binom 7 through 10 of 10.5. Okay, and so using R, the answer that I get is 0.1719. Okay, so this adds up to 0.1719. So this is from R. You can verify, but okay. Does this answer make sense? So if someone plays casino coin flip 10 times, what's the probability that a random person will win 7 or more games out of 10? The probability of that happening is about 17%. Okay? So about 17% of players who play 10 games of casino coin flip will win 7, 8, 9, or 10 times. So if they're willing to accuse me of cheating because I won 7 games out of 10, that means they would be accusing approximately 17% of players who are playing fairly of cheating. Does that seem like a lot of people to be accusing of cheating? It does, right? That's over 1 in 6, right? It's like saying if you roll the number 6 on a die, I think you're cheating, okay? It seems like a lot of people to be accusing of cheating, because those people, a person playing fairly, if they play 10 games, there's a 17% chance that they're going to win 7 or more games out of 10. So the answer to our question, how likely are we to observe this data if the null hypothesis is true, is it's quite likely. Okay, it is likely for us to see the data, even when someone is playing the game fairly. Okay, so because this number is quite high, the probability of our data is quite high, we would say we don't have enough evidence to accuse someone to I guess, convict someone of cheating. Does that make sense? Okay, this probability is high, so we shouldn't jump to the conclusion that someone is cheating. Okay, does it prove that they're not cheating? It doesn't prove that they're cheating. So, someone could very well be cheating in increasing the probability of winning, but they're smart enough to just stop after 10 games, so it's inconclusive whether or not cheating actually took place. Okay? So, so the answer, our conclusion here is, because this probability is high, we do not have evidence that the player is cheating. Okay? We do not have evidence of cheating. Okay? And it's important that we say we don't have evidence of cheating. Okay? Because we don't have evidence. Yeah, we don't have evidence of cheating, but it also doesn't prove that they're playing fairly. Okay? So don't say this means that the guy's playing fairly. It doesn't. It just means we don't have evidence of cheating. Okay? Even if the guy were to win exactly 0.5 of his games, it doesn't prove that he's playing fairly. He could be cheating, but just not doing a good job of it. Right? And so, if you ask casinos, am I allowed to count cards? They'll say, technically, yes. They discourage it. And if you're caught counting cards, they might ask you, please don't come back and play. But it's not illegal to count cards. And a lot of times they don't mind, because most people who count cards do a bad job and they end up making their money anyway. So, anyway, as much as I know about statistics, I still enjoy playing the occasional game of chance. So, okay, so on the other hand, let's say you stick around and you play 100 games, okay? So in the previous slide, we played 10 games. We're expecting you to win 50 or 5, and you won 7. Okay. So this time you're going to play 100 games of coin flip. Okay. We expect you to win 50 games. You actually win 70 games. Okay. And so now the manager comes back out and he says, you're winning too many games. I think you are cheating. Okay. And so what do you say? No, I just got lucky. All right. So the manager says, okay, smart guy. Let's, if I give you the benefit of the doubt, exactly how lucky do you have to be? Have to be to win 70 games out of 100. That's what we want to know. Okay? So again, we're setting up a pair of hypotheses. Null hypothesis would be no cheating, or in other words, probability of a win is 0.5. And then the alternative is that even though we don't know exactly what's going on, cheating is taking place, probability of winning somehow has become more than 0.5. So we're not playing with a fair coin anymore. Something's going on, and we want to know. Okay, so we're going to just say, all right, let's, for argument's sake, say you aren't cheating. Let's say the game is fair. Well, how likely is it that a person who's playing the game fairly will win 70 games out of 100? Okay? And really, what we should be asking is 70 games or more, because we're asking what's the probability of seeing the data, which is winning 70 games out of 100, or something more extreme if the null hypothesis is true. Okay? So we're going to ask, what is the probability of observing our data or something more extreme if we assume that the null hypothesis is true. Okay? So my defense again, they say, I think you're cheating. I just say, no, I just got really lucky this time. You know, I won 70 games out of 100. I'm just on a lucky streak right now, okay? I love Vegas. You know? And then what's that? And they say, no, I don't think you're this lucky, okay? We're going to say, okay, well, let's just say you were lucky. Let's say you're playing fairly. How lucky do you have to be? How likely? What's the probability that someone's going to win 70 games out of 100? And we're going to say, you know, and we'll say 70 games or more out of 100. So we could answer this using normal approximation to the binomial, or I'm just going to have R calculate it for me. Okay, so I'm going to just say my R command will be what? In R, I'm going to write sum of d binom 70 to 100, 100.5. Does that make sense? So I'm going to take the d binom for 70, d binom for 71, d binom for 100, all the way up to 100, and add them all up. So I'm going to punch that in. What is the sum of d binom 70 through 100, 100.5? Okay? And I'm using regular old R here, not RStudio, just because for simple calculations, well, R loads faster than RStudio does, okay? Just because there's less bells and whistles. And for simple calculations, I think R is good enough. If I'm dealing with a data set or doing a little bit of programming or anything like that, RStudio I prefer, okay? But anyway, so I do this, and my answer is 3.925 times 10 to the negative 5. 3.925 times 10 to the minus 5. So if you remember scientific notation, that means we're moving our decimal place 5 spaces to the left. 3, 4, 5. So my answer ends up being 0.0000392.5. So it's 3 in, or about 4 in 100,000, is that right? So it's approximately 0.123404, which is 100,000, 10,000, 100, yeah. 4 in 100,000, okay? 400 thousandths. Or 1 in 25,000, approximately. So does my I just got lucky defense seem pretty good? No. So the casino boss can say, either you really are lucky, you're one of the 1 in 25,000 who happens to get 70 wins out of 100 by playing fairly, or you're doing something sneaky and you're cheating. And either of those are completely valid possibilities. I could actually be 1 in the 25,000 people who happen to get 70 wins out of 100. But what does your intuition tell you? Your intuition says that's probably not the case here, right? You know, if I had to take a risk, I would say you're probably not 1 in the 25,000. you're probably doing something, I don't know exactly what, but I think you've somehow changed the probability of winning to be greater than 0.5. Okay? So because this probability is so small, okay? Or, yeah, let's write that. This probability is tiny. Okay? So we conclude, okay, the fact that we observed this data, okay, the fact that we did see 70 wins out of 100 causes us to doubt the null hypothesis. So we conclude that the null hypothesis is false, and we say we have evidence that the probability of a win is now greater than 0.5, which in other words is there's cheating. Okay? Now, the truth is, well, we don't know the truth. The truth is, it is technically still possible that I am playing fair, and I did happen to just get extremely lucky. And we'll never know the truth. If, you know, in all of life, as you do these hypothesis testing, okay, in statistics, we can't guarantee the truth. But we can say, based on what we know about probability and how likely our data is to appear, because the probability of us seeing the data that we see, 0.000, 70 wins out of 100, because that probability is so low, we can come to the conclusion and feel safe about saying, I think cheating is going on. Okay? So we can say we have evidence of cheating. So we can say that. We do say we have evidence of cheating, even though the truth is it is technically still possible that we are playing fair, but we just happen to be in this really freakishly odd situation. Okay? And that's a lot of times how you go about life, right? You come across a thing and you say, wait, what's going on here? You know, what happened? And maybe you hear two different stories, okay? And based on one just sounds more likely than the other, okay? Is it possible that the more far-fetched one was actually the truth? It's possible, but because it's so far-fetched, your brain basically is assigning a probability value and saying, I guess that's possible, but the probability of that happening is so low, I don't believe this story. I'm going to go with this story which just sounds more likely. Okay, but the truth is the far-fetched one could have been the actual truth. Okay. What's that?
Oh, I just finished Serial.
Yeah. So yeah, Serial, excellent podcast. Yeah, in the last episode they talk about, you know, if we were to assume, you know, he was innocent or something, you know, what's the probability, you know, how likely is it for this sequence of events to happen? And a lot of times that's what prosecution cases use to say, it seems really far-fetched for this strange sequence of events to happen, or whatever, okay? And, you know, regardless, that could be the case. It might not be. We don't know. But yeah. So anyway, that's essentially what hypothesis testing, how that goes. Okay. So let me just we'll put up some important terminology here. Okay. So we have the null hypothesis. which we write H0, okay? And there's always going to be a pair of claims that go together, okay? So the null hypothesis, and we'll get into how to assign these, the null hypothesis will always have an equal sign in it. Equal sign in it. Okay? And then you have the alternative hypothesis. Okay? And it will look identical to the null hypothesis, except the equal sign has been replaced with either a not equal or a greater than or a less than, okay? So whatever the hypotheses are here, you've got a null hypothesis, which will have an equal sign, and then the alternative hypothesis will be identical, with the exception that the equal sign has been replaced by a greater than, less than, or not equal sign. Okay? So just flipping back a slide. Here I said cheating is that no cheating going on means the probability of winning is equal to 0.5, which is what we would expect for a coin flip game. And then the alternative hypothesis is that the probability of winning is greater than 0.5. So these two are identical, except we've replaced the equal sign with a greater than sign. Okay? So you're going to have a null hypothesis and an alternative hypothesis, okay? You do the math and you arrive at something called a p-value, okay? And we're going to talk about p-values all the time, and I know we've already have a billion p's already, p probabilities and p for the binomial and p this and whatever, okay? Here's another p-value, okay? And it's just when you're dealing with statistics and probabilities, and we have probabilities of everything, we're going to have a bunch of p's. And I apologize, but this we always write p-value. Well, I mean, not always. In reports, sometimes it just says p is greater than this, and you have to assume that they're talking about a p-value. So, but at least okay. So anyway, the p-value is the answer to the question, what's the probability? So I'm going to just say the p-value is the probability of observing our data, or something more extreme, if the null hypothesis were true. Okay? So we are assuming that the null hypothesis is true, and we're doing calculations, and we're calculating what is the probability of observing our data. So in our previous example, if we assume that the player is playing fairly, which is what the null hypothesis states, if we assume the null hypothesis is true, what's the probability of observing our data? And we had two examples. In one case, what's the probability that someone wins 7 games out of 10, or something more extreme, so being 7, 8, 9, or 10 games out of 10? And it turned out the probability of that is high. On the other hand, in the other example, we did what's the probability of somebody winning 70 games out of 100, or something more extreme, 70, 71, 72, all the way up through 100 games out of 100, and the probability of that was quite low. Okay, so that is the p-value. And we have conclusions. And the conclusions are either the p-value is large, or the p-value is small. Leave a little space between these things, okay? So we have over here to decide what is a large and what is a small value. When you start off, before you do your test, you should have something called an alpha, or significance level. Which is equal to some number alpha, an arbitrary number, and we'll talk about this in detail next week or the week after. So p-value large means the p-value is bigger than alpha, and p-value small, p-value is less than alpha. So the p-value is a probability, so p-value is always going to be between 0 and 1, and your alpha is usually 0.05, but technically any value of alpha is acceptable. But generally, to get published, you need something 0.05 or smaller. That's somehow become the gold standard. But anyway, that's how we decide if the p-value is large or small. So if the p-value is large, your conclusion is okay, so we're going to write, even if the null hypothesis, let me think. Sorry. I just want to word this in a way that makes sense. Okay, so even when the null hypothesis is true, okay, we have a non-negligible chance, non-negligible probability of observing our data as a result of random chance. Okay? So even if a player is playing the game fairly, the probability of them winning 7 games or more out of 10 is non-negligible. We can't ignore that. There's a 17% probability. Okay? So we do not reject the null hypothesis. That is if the p-value is large. Let me just draw a line to separate when the p-value is large from when the p-value is small. On the other hand, if the p-value is small, we will say, what we say here is that if the null hypothesis is true, the probability of observing our data as a result of random chance alone is so small that we are willing to rule out the possibility that it happened by random chance. Okay? So we conclude, or we decide, I should say, we decide to reject the null hypothesis. Okay? And we say we have evidence. We have evidence to reject the null hypothesis. So these are the conclusions that we can make based on our p-values. Okay? So this sets up the framework of hypothesis testing. Okay? So keep that kind of logic in mind. And next week we'll get into the actual mechanics of doing a hypothesis test for, I guess, one of our simple cases, which would be the t-test. Okay, so next week there's no book homework assigned, but next week the Lab 2 assignment is due. Okay, and so I tried to record the video last week of how to do it. If you get stuck or have questions, send me an email. If you encounter error codes, you can search for them on Google, or you can send them to me, and I'll try to help you out also.